teaching is an emerging discipline where we aim to build interfaces for human teachers to teach machine learners. The central idea is that we want to allow non-machine learning experts to teach concepts to machines using an interactive interface. This can lead to lower costs in creating ML models while improving their performance.
In our research, we have proposed a machine teaching framework that consists of three main components: a teaching interface, a machine learner, and a knowledge base. These components service each other and contribute towards the goal of machine teaching. The teaching interface describes the machine state exposed to the teacher and the human feedback that will be asked from the teacher. The machine learner describes the feedback interpretation and the machine learning algorithms at play. And finally, the knowledge base describes the domain knowledge and task-specific knowledge used by the system. We want to minimize a twofold objective. First, we reduce the error by allowing granular feedback and combining it with knowledge. We also use an adaptive machine learner that prioritizes confusing examples using active learning. Second, we also want to minimize the human effort by providing machine state to the human teacher using ideas from interpretable machine learning, and using the knowledge base to assist human teaching. Our work is focused on the task of intent classification for Jill Watson systems deployed in real-world classroom settings. An input to Jill Watson is classified into different intents for downstream processing in order to generate a response. Our aim is to use machine teaching to teach the task of intent classification to a machine learning model. Machine teaching can be very helpful in systems like Jill Watson, where multiple machine learning models may need to be trained and deployed as part of a bigger application. Each individual system can have a machine teaching interface, where a subject matter expert can teach the machine to improve its performance using accumulated, unlabeled examples over time. In machine teaching research, we also focus on human-AI interaction design, involved in realizing the teaching interface for these systems. From the AI side, we wish to provide a machine state to the human teacher to build an accurate mental model of the machine in the teacher's mind. This is done by employing interpretable AI methods that can be used to help teachers in performing teaching tasks on the interface. From the human side, we wish to keep teaching tasks simple and easy to perform. The teacher should be able to interpret the machine state and use it to minimize redundancy in their feedback. Now, we'll show you a demo of our machine teaching system for the task of news article classification, which is simpler to follow without going deep into the details of intent classification for a complex system like Jill Watson.
We can see the examples that are confusing for the machine on the left side. Let's select one of them. You can see that machine is giving the current prediction for each of these classes. Based on this text, I can see that the class should be business. So I'll select business. I can also check the label guide provided here to see if my label is correct. Now I have to select inconsequential words, that is, words that are not important in determining the business class. So I'll select posted and maybe US. I have to select words that are important in determining the business label. The word profit is important. The word market is important. Now I have to suggest replacements for the word profit that preserves the class business. And now I have to submit the words that can replace market and preserve the label business. And I submit the example. In the backend, the machine will use all the information I provided to perform a data augmentation process and train a new model that can give updated predictions. We can refresh here to see which examples are the most confusing. With recent progress in large language models and their increasing capacity to perform well at zero-shot learning, we've started exploring how humans can work with ChatGPT-like tools to create models for complex and modular ML systems employing multiple API services. With zero-shot learning, one can instantly deploy an NLP module by intelligently constructing a prompt and making an API call. After deployment, these modules can collect examples passing through them, and construct a dataset of their own. We want to know if you can use these datasets to improve the system with some human intervention. This data is not perfect, but we do have initial noisy labels thanks to our intelligent prompting. There are many methods to find mislabeled examples in a noisy dataset, so a human labeler can possibly focus only on examples that are likely to be mislabeled instead of looking at the entire dataset. And understanding where the zero-shot learner is struggling can be useful in several ways. We can provide zero-shot learner with examples to improve its performance, or simply use this new dataset to train a model that can now replace the original prompt plus API call.
This is early research, and there's lots of ideas to explore and to evaluate. The excitement around the power of large models in language and other modalities is leading to an explosion in the number of new, complex machine learning systems being deployed to an ever-growing set of applications and domain areas. It's more important than ever to empower non-machine learning experts to use and evaluate those systems. We're excited to continue exploring the role machine teaching will play in this broader landscape of artificial intelligence research and use.